We just got done talking about making Kevlar, where we're making an amide bond, and talked about making an amide that we usually use a carboxylic acid chloride and an amine because it is an easy, quick reaction. But sometimes we can't do that, and so sometimes we need to use a carboxylic acid and an amine instead of an acid chloride. So if this is our amide that we desire to make, then the amine would come in, kick out the OH, and form water, and form the amide. But the complication is, again, that a much faster reaction, a reaction between the base and the acid happens, and we end up getting a salt, which is undesired. So this is the faster reaction. Instantaneously we dump these two things together and we end up getting the salt. And so because the reaction, we're saying this reaction is faster, that means that it has a lower activation energy. And what we can do here is draw an energy diagram where we have the reaction and then the free energy as a function of the reaction. So if we start out, trying to get it to focus a little better here, if we start out with A, where we're wanting to begin, and we are going to form B, it turns out that B is actually lower energy, more stable, and more thermodynamically favored. You've heard that term before. Turns out that the salt, which forms instantaneously, is lower energy than A is, but not as low energy as B. It forms fastest, and it is then known as the kinetically favored product. So what would this look like on an energy diagram? We said that B is lower energy. I probably should have drawn A a little bit higher here, but B is lower energy than A, and also B is lower energy than C is. So we will make C here, which is a little bit lower energy than A, and B that is quite a bit lower energy than A. So we're saying that in this reaction, we're just going to draw one hump in the reaction. It's actually, it is only one hump in the, there's only a transition state and one step going to form the salt, but there are multiple steps going to form the amide. So if we say that the first step has a small hump going to form the C, and the first reaction going to form the salt actually has a small hump, then it takes a greater activation energy to get to B. This is a slower reaction. So this is the fast reaction, the product from the fast reaction. This is the product from the slow reaction. So dump the stuff together at room temperature, boom, we get nothing but the salt. Then we start putting energy in. We start cranking up the energy, putting enough heat in there so that we have enough energy to go forward and backward over through all of the transition states, or forward and backward through both of these pathways. Then it reaches equilibrium. When it reaches equilibrium, when we're at an equilibrium state, what is going to be the major product or major reactant? A, C, or B? Again, the thermodynamically more stable, the lowest energy will be favored at equilibrium. And so if we want this reaction to happen and favor the product that we want and not the salt that we don't want, then we need to do it at high temperature. And thermodynamically favored means that we need to do it at high temperatures. Sometimes we can't get to the temperature that we need in a normal flask that is open to atmospheric pressure, and we would have to put it into a reactor. And when we're doing things on industrial scale, it's pretty easy to get to high pressure. You have huge stainless steel reactors that can be sealed and then cranked up to whatever temperature is necessary, keeping it under high pressure, and we can get above the temperature that all the reactants would normally boil at. So I just wanted you to think through this equilibrium that was involved here and go back to our discussion earlier in the course in the first semester about kinetics versus thermodynamics. And sometimes a product is both kinetically and thermodynamically favored, and sometimes a product is kinetically favored but not thermodynamically, and vice versa. And if we have a product that is thermodynamically favored and we can do it at high enough temperatures, then we can drive the equilibrium in and force the reaction to go in the direction that we want.